First, a little disclaimer. This is not a tutorial. This is the quick solution to the final exam of April 2012. The first question was on phasors and second-order systems. In the circuit below this one, switch A has been closed for a very long time and switch B has been open for a very long time. That means the circuit is in steady state. The source is AC, the circuit is in AC steady state. We can use phasor analysis. Well, we need to find the current in the inductor. The current here, this current, and we need to find that as a function of time. But we can find that first as a phasor and then write that current as a function of time. Find also the voltage in the capacitor, this one, as a function of time. We do the same, find that voltage as a phasor and then write that as a function of time. So let's begin. Because we will be using phasor analysis, the source, which is given by this function of time as 141 sine 400 t volts, is going to be represented by a phasor. So we turn that function of time into a phasor. RMS value of this voltage is peak value 141 divided by root 2, and that is approximately 100 volts. The phase of that sinusoidal wave is 0 degrees, so the phasor is 100 with 0 degrees of volts. If you use the actual value, which was in the vicinity of 190 something, that is correct. So this is a roundup. The reactive elements, the inductor and the capacitor, will be represented by their impedances. So the 10 millihenry inductor is going to be represented by J omega L. Omega is 400 radians per second. That impedance is J 4 ohms. So this inductor will be represented as here by that J 400 ohms impedance. The source is this 100 with 0 degrees phasor, which is a real number, just 100 volts, the RMS value of that source over there. And the capacitor also is represented by its impedance, which is negative J1 over omega C, omega 400 radians per second. And the impedance of the capacitor is negative J3 ohms, like so. We are ready to solve this circuit. We are in the phasor domain now. We use a money. Let me move the screen a little bit, like so. Reference node, node number 1, branch currents. Chosen arbitrarily. We solve the circuit. We need only one KCL equation for node 1. Currents going in, this one. 100 minus V1 divided by this impedance 4,4. 100 minus V1 divided by 4,4. That is equal to the currents leaving the node. This one, V1 over 3, and this one, V1 divided by the impedance 3, negative 3. From there, we solve for the voltage of this node, V1, as a phasor, 28 volts with negative 49 degrees approximately. That is that voltage. But that is not what we need to find. What we need to find is A, the current in the inductor, this one, and B, the voltage in the capacitor, this one. How do we go from this value, this voltage, to that current and that voltage? Well, this current is the first term of our KCL equation. So now that we know what is V1, we use that formula and obtain the current in the inductor. 100 minus V1, given by this expression, divided by the impedance of the branch, 4,4. That is 14.9 amps with negative 30 degrees. That is the current in the inductor flowing from left to right as a phasor. And the voltage in the capacitor is given by a voltage divider. The total voltage V1, given by this one, multiplied by the impedance of the capacitor and divided by the total impedance of the branch, 3, negative 3. That is 20 volts with negative 94 degrees. But the question is asking us to write that current, this one, and that voltage, this one, as functions of time, not as phasors. So we translate those into functions of time, and we know how to do that. The current in the inductor as a function of time has the peak value, this RMS value multiplied by root 2, sine 400t. Why 400t? Because the frequency is the one of the source, 400 radians per second, minus the phase, 38 degrees times pi divided by 180 to make that into radians, and those are amps. And the voltage in the capacitor is 1996 root 2, that is the peak value of the voltage in the capacitor, sine of 400 radians per second times t, minus 9381 pi divided by 180 volts. But there was one more question. Let's see. Let's go up there. Part C. Find what is the average power delivered by the source in watts. That is also known as active power, P. Well, we know how to compute that. Absolutely. The power here was the RMS of voltage times the RMS current, which is IL 1487, multiplied by the cosine, let's see it down here, RMS volts, RMS amps, times the cosine of whom? The cosine of the angle of the voltage minus the angle of the current, phase of the voltage 0 degrees minus phase of the current from here negative 30 degrees. That is 1283 watts, and that completes part A. Let's stop now, and in the next video we'll target part B of this exercise. Thank you very much.